Okay, here we are, lesson 12, so we're going to be looking at the normal distributions. So we're finishing up looking at a lot of the really popular continuous distributions. Normal. The normal distribution, here are just a few examples here. It is probably one of the most commonly used distributions in statistics. You read research and people talk about, oh, getting a z-statistic and a p-value and whatnot. They're using a normal distribution. Super common distribution. I would argue it's one of the more important ones. It's a stepping stone. Like in theory, this is a great one to use. In practice, we will investigate how using it works. But some aspects about it. It is going to be a distribution. It is perfectly symmetric. So if you fold it in the middle, it's going to be perfectly symmetric on both sides. It goes on forever in both directions. It has a single peak, or unimodal is one way we will call it, and it's bell-shaped. So it has this bell shape. And here are just a few examples. We describe it by two parameters, mean, mu. This tells us where it's going to be centered, and standard deviation, sigma. So this is going to tell us how wide or narrow it's going to get. So here, let me see. None of these have all the same. But like we have a mu of -3, so it's centered at -3. And then we have sigma of 0.5. Here, mu is 1, so our center is shifted over. Sorry, mu is 0. So our center has shifted over to 0. We've increased our standard deviation, so you'll notice that the blue curve is wider than the orange. It's also a little bit shorter, and that comes down to the area under the curve has to be equal to 1. No matter what PDF we're looking at, the area underneath has to be equal to 1. And so as you can see, you make sigma bigger and bigger, it's going to get wider and wider. So we have, if we have a random variable that is normally distributed, so x is normally distributed, you can write it as this equation right here. And you'll notice, I mean, it's a little gnarly for sure, and 0 else. So basically, as long as x is a real number, it could be anywhere, negative infinity to positive infinity, this is going to be the equation. So this is what I was saying is it does go forever in both directions. Just know that as you get really far out in the tails, the area gets really tiny, but it's never exactly equal to 0. And if we have a normal distribution, we know the center is mu. What's really cool is the expected value. The mean is also the median here. And then the variance is equal to sigma squared. So if you want the standard deviation, you're just going to go ahead and square root it. So just some iterations here. So mu, sometimes I'll write, so this is the Greek letter mu. Mu, occasionally I'll write mu of x. So if I said, hey, x is my random variable, the mean of that random variable is mu x. Sigma, so this is sigma. Like I said, with I think accepting the uniform distribution, most of the time when we have parameters to describe the shape, scale, location, whatnot of a distribution, usually we will use Greek letters for this. And once again, I might say sigma of x. Just know if I say sigma of x, I'm just saying, hey, the standard deviation of the random variable x. So typically, we are not likely to go ahead and say, oh, well, I want to know from, if I want my PDF x to, sorry, negative infinity to x, I'm not going to throw this PDF into an integral. And in part, it's pretty gnarly. Absolutely, you're welcome to do it. I've done it back in the day. It's one of those things that if you do integrate this equation, usually it's something you only do once. I had a master's course, they had us do it. It was gross. We had to switch to polar coordinates. I've heard of other ways to do it. It's still pretty gross. By and large, we have other ways around it. If you've ever used a normal table, that's one of our ways that we work around it. Also, we have, just calculators and computing programs like R. So we don't need to integrate this by hand. Thank goodness. So that's just us saying we don't like to integrate it. It's gross. So once we have a normal distribution, there are some neat features about how the spread is set up. So if you have this center here, mu, and you can calculate, okay, well, if I'm, one standard deviation in either direction, you could find, using this 68, 95, 99.7 rule, I've also heard it called the empirical rule, the middle 68%, like if you go mu plus and minus 1 standard deviation, you have roughly the middle 68% of the data. It's an approximation, it's not exact, but it is roughly the middle 68%. So 1 standard deviation, 68. If you go 2 standard deviations out in either direction, that's roughly your middle 95%. And once again, this is an approximation. And then you go out 3, that's going to be roughly 99.7%. So know that if you go out here in either direction, there is area in those tails. It's tiny, but the area in those tails is not equal to 0. So be careful, you don't want to leave that out. So in general, if you know, it's distributed normally. So we like to say, okay, well, our random variable x is simulated normal, and then we like to say, oh, whatever the value of mu is, and then the standard deviation. This would be a shortcut way that we like to write, hey, this means the random variable x is normal with a mean of mu and standard deviation of sigma. Once again, you would replace mu and sigma with actual numbers. So, yeah, definitely a very handy rule. Things to note, you can only use this rule if you are an exact number of standard deviations away from the mean. It will not apply if you're 1.5 standard deviations away. You cannot use it. It has to be 1, 2, or 3 standard deviations away from the mean to be used. So we're going to go ahead. We have an example here. We're going to practice using the empirical rule. So a lot of civil engineers especially really focus on bridges and traffic. Definitely has a lot to do with maintenance and how they're built. It's really important to know what kind of traffic a bridge might see. So they're going ahead, they're investigating vehicle speeds on this bridge. They determine the average speed on this bridge is about 58 miles per hour. I don't know about y'all. I haven't been on a lot of bridges where the speed limit's even close to that. It makes me a little nervous, but whatever. I'm from the Bay Area, so maybe it's just traffic. And so it's less probable the further away. So one thing to think about is my average is 58, and it's less probable further away. So as you can see, the peak is here. This is where the highest probability is. But as you go further out, the probabilities get smaller and smaller. So that's one way we would describe it. And the distribution of speeds, we're going to even assume it's normal, not just that symmetric, with a standard deviation of 10 miles per hour. So it's going to ask us what are the parameters for the distribution. So we're assuming it's a normal distribution. So that means we need mu, and I'm going to even write mu of x, because x is vehicle speed. So mu is going to be that 58 miles per hour. I like to label the units here. Sigma of x here, that's going to be that 10 miles per hour. So draw the distribution by hand. You might notice I kind of cheated a little bit. I drew or included a curve right there. Most of the time, like especially if this were like an in-class thing, it doesn't have to be a perfect bell curve. We're not judging you on how beautifully you can make your normal distribution. But it has to be recognizable. It has to be something where like, oh yeah, they were definitely trying to draw a normal distribution. So I put my units here, and then it wants me to write out mu plus or minus 1 standard deviation, mu plus or minus 2 standard deviations, mu minus plus or minus 3. What that means is it just wants me to label all of these tick marks. That is all that it's requiring. So for me, I tend to do addition a lot better than subtraction in some cases. 10 is pretty easy, so each tick mark here should be 10 apart. So 58, 68, 78, 88. And then I can go the other direction. So 48, 38, 28. And just note that it does go forever in both directions, so eventually it will get to negative values. But the area out there, the probability is so tiny that we're not really too concerned about it. Just know that it can happen. It also can go forever in that direction, but once again, the area gets really, really tiny. So we're not too concerned. So now that we have this drawn out, we're going to see about using this distribution to calculate some probabilities using the empirical rule. So we have same problem. We want to know, we randomly select a vehicle driving on this bridge, and we know it's distributed normal 58, 10. And I'm going to just put miles per hour there. We want to know what's the probability that I randomly selected a vehicle that's between 28 and 68 miles per hour. So I'm going to at least write out the ones that I want. 48, 38, 28. So I want between here and here, in the middle, and 68. So for me, I am going to break this down into two parts. I'm going to find the area of this wedge and the area of that wedge. That's how I'm going to do this. So things to consider. 78, 88. If I had wanted from 28 to 88, I would have known that this entire area is roughly 99.7% of the area, or 0.997. If I fold it in half exactly on this middle, so I don't want this half, I just want this half. This is 0.997 divided by 2. So that is my argument there. So my wedge 1, so 0.997 divided by 2, that's my first wedge, plus, now I'm going to get my second wedge ready. So if I had wanted from 48 to 68, that's one standard deviation in either direction, that's my middle 68%. But once again, if I fold it in half and only take this half, and it's really important that you have to fold it in half down the middle. You can't fold in half anywhere else. It won't work. Now I have that 0.68 divided by 2 in that wedge. So 0.68 divided by 2. So I want these areas. I'm just going to label them here. So 0.997 divided by 2. I'm going to use a different cross-hatching here. So this one will be 0.68 divided by 2. So I can go ahead and simplify these a little bit. This is what, 0.4985, maybe. Okay, plus 0.34. So adding those together, I know I had a calculator, but I'm not sure where I put it. Just a second. It's 0.85 over here. 3. No. Yeah. So about the middle, 83.85%. So there's, if I randomly select a car on this bridge, the probability I selected a car going between 28 and 68 miles per hour is going to be about 0.8385. And then the probability that I'm going more than 78 miles per hour, so if I'm listing here 78, so I am a big fan of drawing it out so I know exactly which area I want. So there are a couple of ways I could do it. For me, I'm going to break it down into, I know the area of this half, hint, half, and then I could find the area of just this wedge right here. And I can go ahead and I can subtract those from 1, and that will leave me with the area in that little wedge. So I'm going to count the area here first. So once again, I went ahead and I went from 38 to 78. That's 2 standard deviations in either direction. This would be my middle 95%. However, if I cut it down the middle and I only take this half, that's going to be 0.95 divided by 2. Now this wedge, it's a full half, so that's just 0.5. So if I want the area, so this third part, 3 is equal to 1 minus my first wedge minus the area in the second wedge. So my area will be 1 minus 0.5 minus 0.475. I'm going to end up getting 0.025. So it looks like, according to the empirical rule, about 2.5% of the time that I randomly select a car, I'm going to randomly select a car or a vehicle that's going above 78 miles per hour. Which, I don't know what kind of bridge this is. It seems kind of risky to me, but it seems like this bridge is built for it. So we're going to continue on. We're going to talk about the scenario where we do not know an exact number of standard deviations away and work from there. We're also going to be looking at percentiles. So fun stuff, introduce the z-table, lots of practice available in the your turn questions, and we'll see you in a few.